So the first quantum number we're going to look at, again, think of quantum numbers as like the address of an electron, is something known as the principal quantum number. If we're going to look at this model of an atom kind of like an electron hotel, this would be the floor that the electron is located on. And so the principal quantum number, we use the letter like a lowercase n. That's the principal quantum number. Gives you an idea of the overall size and energy of the orbital. So think of it like this. So here we have increasing energy, and n can have any value, any whole number value of one or greater. One, two, three, and so on and so forth. Nothing less than one, no decimals or anything like this. And as that number increases, n equals 1 is the lowest energy. And then you have n equals 2, and then n equals 3, and so on and so forth. One thing to note is that as n increases, the gap between n levels, so like between 1 and 2 or 2 and 3, that decreases. And something else important is the distance from the nucleus increases as n increases. Now, if we kind of compare, let's compare what n equals 1 to is, might be this. N equals 2 is going to be bigger, and then so on and so forth. So if you look at this diagram on the right, these represent like n equals 1, n equals 2, n equals 3. Don't worry about this S yet, 1s, 2s, 3s. We will get to that. But I want to kind of highlight here that the colored regions you see there, so like this little blue right here, well, maybe I'll do it in blue and not red. So this blue dot right there, that represents the probability of finding an electron. And then n equals 2. So what that red sphere is showing, so here's n equals 1. And then the red part there is n equals 2. So notice how that energy, it's farther away from the nucleus, and it's a much bigger probability. Now, one important thing I want to highlight that we didn't see with n equals 1, I'm going to zoom in. Look at this empty space right here. Well, the highlighter's not really letting me do it that close. But kind of look at that empty space around the blue, but right between the blue and the red. That empty space is known as a node. And a node is a region where you will not find the electron at all. Definitely will not find it. And so if you look at this kind of this XY graph down here, this little valley where it hits the y-axis, or I'm sorry, the x-axis, that represents a probability of 0. So the probability of finding an electron there in that position, in that node, is 0. And if we go to n equals 3, so again, there's that node between 1 and 2. There's the node between 2 and 3. And so at n equals 3, there are 2 nodes. Now, one of the cool things about the periodic table is that you can look at the table and instantly know what that highest energy level is for any atom on the periodic table. And all you got to do is look at the row. So for helium, I'm sorry, for hydrogen and helium, its highest energy level is 1. There's no other energy levels. Starting with lithium, all of these atoms, the highest energy level is 2 and 3, and so on and so forth as you go down a column on the periodic table. Now, this will become a lot more helpful when we start putting all of the quantum numbers together so that you'll be able to describe any single electron inside of these atoms. And so again, just to kind of review, n, or the principal quantum number, is about the overall size and energy of the orbital. Now the next one we're going to look at is known as the angular quantum number, or we use this like a cursive lowercase l. This basically tells you the shape of the orbital. Again, I want to highlight what an orbital is it's a mathematical solution. And that mathematical solution forms a shape that can be graphed on like an X, Y, Z coordinate, kind of forming a three-dimensional shape. Now, the allowed values of L can be 0, 1, 2, and so on up until you get to n minus 1. So for example, if n equals 1, remember that's the lowest energy level, that's the only value of n you can have. Well, what's n minus 1? 1 minus 1 is 0. So the only value allowed for L is 0. If n equals 2, well, then the allowed values for L are n minus 1, which is 1, and anything less than that, and 0. Well, what if n equals 3? So the highest L can be is n minus 1, which is 2, and anything below that, 2, 1, and 0, and so on and so forth. Now, to describe these shapes, what we're going to do is we're going to take those numbers for L and assign them a letter. 0 represents the letter S. 1 represents the letter P. 2 represents the letter D. And if L is 3, that represents the letter F. Don't need to worry about going any higher than that. This class, that's outside of the focus of this class. Now, the shape that corresponds to for S, that's a sphere. Now, I know I just drew a circle, but imagine a three-dimensional sphere. The shape for P is a dumbbell, and it's oriented in 3 directions. You have up and down, so like on the y-axis, you have it oriented on the x-axis, and you have it oriented on the z-axis coming out at you. So kind of imagine this dumbbell is coming out at you. So you have this x, y, and z-axis. Now notice that for S, there's only one orbital in what we call the S subshell. There are 3 orbitals in the P subshell. Now the D orbitals kind of look like a 4-leaf clover, and I'm not the best at drawing that. But you got 4 of those. And then there's one more that kind of looks like a dumbbell with this ring around it. Kind of weird. Again, we're dealing with quantum stuff. Quantum stuff is weird. And so you have a total of 5 orbitals, the 4 4-leaf clovers, and then the one dumbbell ring in the D subshell. And the F subshell Um, I'm not even going to try to draw them. Just know that there's like seven of them. There's seven f orbitals in an f subshell. Again, I've said this before, I'll keep on saying it. An orbital is just simply a mathematical solution of the Schrodinger equation of where you can find an electron. So this kind of shows you the shapes of the orbitals better than what I can draw. So notice here's like the s orbital. Again, there's one of them. Okay, so in an s subshell, there's only one orbital, and these represent the p orbitals. Notice there's three of them. And I want to highlight this also, that the orbitals in a subshell, so like in the p subshell, are all degenerate. That's a term I've used before. They're all equal in energy. And then here's our D subshell. So you got five of them. So they all kind of, we got four of them that look like a sort of like a four-leaf clover. And then you got this weird one right here. And then F, you got seven of them. Don't worry about having to draw any F orbitals, but you should know what S, P, and D look like. So you should be able to kind of draw or recognize those orbitals. Now, just like I did with the principal quantum number and how we were able to easily find that using a periodic table, we're going to do the same thing here. So how does this angular quantum number look on a periodic table? Okay, well, these first two rows here, and we're going to include helium in this, are what we call S block elements. I'll tell you why we call them that in a little bit. It'll be, like I said, most of this will become clear once we put it all together. And then these here that I'm highlighting in orange, we call them P block elements. And then these I'm highlighting here in purple are called D block elements. And then these I'm highlighting in red down here are F block elements. So start kind of, you don't necessarily need to commit it to memory, but like start, thinking about how these, we can use the periodic table to look at these trends, both now or for what we talked about first with the principal quantum number being on the rows, and then being able to organize the periodic table into these blocks for S, P, D, and F. Now, the next quantum number we're going to look at is the magnetic quantum number. And this refers to the orientation of an orbital. We're primarily going to use this as to find how many orbitals there are in a subshell. I've highlighted this, but now I'm going to put it to a specific quantum number. So M sub L is allowed to have values of negative L to 0 to positive L. Now, let's do an example here. If n equals 4, what are the possible values of L? So go back a couple of pages. L can be 0, 1, 2, or 3. And again, just to review, 0 meant S, 1 meant P, 2 meant D, and 3 meant F. Now, if L is 0, that means M sub L has only one value, 0. Well, how many S orbitals were there in the S subshell? Go back a couple pages when I was showing you the diagrams there. There's only one orbital. So the number of values M sub L can take tells you how many orbitals there are in that subshell. If L is 1, what are the possible values of M sub L? Well, -1, 0, and +1, which is 3 orbitals. If L is 2, M sub L can be -2, -1, 0, +1, +2. That's 5 values. So there are 5 orbitals in the D subshell. And then finally with if L is 3, M sub L can be all the way from -3, -1, 0, +1, +2, and +3, which is a total of 7 orbitals. All right, and then finally, the spin quantum number, or M sub S, identifies a specific electron in an orbital. Now, M sub S can only have one of two values. It's either +1/2 or -1/2. And I know this is called a spin quantum number. It really doesn't relate to something like spinning around in a circle or spinning like a top. But what this alludes to is something important, is that in an orbital, or I should say, only 2 electrons at most can be in a single orbital. And this leads to what's known as the Pauli exclusion principle, which says no 2 electrons can have exactly the same quantum number or set of quantum numbers. So, for example, if we take helium, helium has 2 electrons. Now, how do I know that? Well, helium has a atomic number of 2 protons. So if it's neutral, it has 2 electrons. Now, those 2 electrons have a different address. One of them, so if we look at where helium is on the periodic table, n equals 1, and then that means L can only be 0. M sub L can only be 0. And then for one of the electrons in helium, it will be plus 1/2. The other electron will have almost all of the same quantum numbers, except its spin number will be minus 1/2. Now, the way we kind of diagram that is, let's imagine, we're just going to say 1s here. The way we diagram electrons having like a different spin, plus 1/2 or minus 1/2, is we typically use an up arrow, like a half arrow for plus 1/2. So plus 1/2 will be the up arrow. And then we use a half down arrow for minus 1/2. You're going to kind of see that notation a whole lot in the coming lectures. Now, let's kind of put this all together. So we said the row tells you the principal quantum number, or I should say the highest energy level. And then we organize them into blocks. So these first two columns we said were like our S block. Now I want you to notice something here. So this was our S block. How many orbitals are in an S subshell? I'm going to kind of pause there. I want you to think about it. One orbital, because that's what an S subshell is a one orbital. How many electrons can I put in at most in an orbital? I can put 2 at most. So look at this here. If I can including helium in this, 1 electron, 2 electrons. 1 electron, 2 electrons. 1 electron, 2 electrons. And I can do that all the way down those 2 columns. I know it sounds a little confusing now, but once we put all 4 of these things together, then it'll become a lot more clear. We look at the P block. So they're in red. Remember, how many orbitals are in a P block? 3 orbitals. Which means how many electrons can the P block hold total? That means 6 total electrons. Now, they're always not going to be filled, but look at how many elements as you go across the row there in red. How many elements are there in the P block? Just pick one row. Oh, 1 electron, 2, 3 electrons, 4 electrons, 5, 6. And you can do that for each subsequent row. Now do this for the D subshell. So I'm not going to, count them all, but notice in the D subshell, there's 10 across. And notice in the F block, there's 14 across. All right, so again, we're using the periodic table here to kind of help us out with these quantum numbers. And what we're going to go into next, and on the next lecture, is how we're going to put all these quantum numbers together. And we're going to use the periodic table to find what's called the electron configuration, or how how electrons are arranged in an atom. How do we put them in particular orbitals? What order do we fill them up? But first thing we're going to do, let's just do some practice, and then that will be it for this lecture. Okay, so in this first problem, identify the subshell in which electrons with the following quantum numbers are found. So letter A, n equals 1. I'm sorry, n equals 3. And L equals 1. Now, first of all, what does L mean? What subshell does that correspond to? That corresponds to the P subshell. So if I'm going to identify specifically that subshell, I'm going to say it is in the 3P subshell. 3 refers to N, the P refers to L. Now for B, N equals 5, L equals 3. Okay, well, what letter did L, I'm sorry, if L is 3, what letter does that correspond to? That's the F subshell. So the specific subshell that this is located in is 5. Again, 5 is for the energy level, and F represents L. And then C, N equals 2, and L equals 0. Number 0 represents S. And so the specific subshell, if an electron were in this subshell, we would say it's in the 2s subshell, or the 2s orbital. Okay, now in the second problem, we're going to just complete this table. Now, we'll just identify here again, N is the principal quantum number. L tells you the subshell, S, P, D, or F. We're going to put a specific number for that, so 0, 1, 2, or 3. M sub L degeneracy, that's just kind of another way of saying like how many orbitals are there equal in energy. So if the orbital is labeled as 4F, that 4 tells you what N is. Now, the way we can get L is by looking at the letter of the orbital. The letter is F. That corresponds to L equals 3. Now, if L is 3, we'll just kind of review. That means that these are the possible values of M sub L. -3, -2, -1, 0, 1, 2, and 3. That's a total number of 7 values or 7 orbitals in that subshell. Now, if you look at the next row, we have to figure out what the orbital is. Well, N is 4 and L is 1. What letter does 1 correspond to? That corresponds to P. Now, if L is 1, the possible values of M sub L are -1, 0, and +1. The P subshell has 3 orbitals that are equal in energy. Now, the next row is a little tricky because, I mean, we can get the energy level 7, that's N. But how do we know what letter it is? We're not given L, but we are given the number of orbitals. And there's only one subshell that has that many orbitals. That's the F subshell. So we would say 7F. And the number for L to represent F is 3. And then finally, on the last row, the number 5 there gives us N. D helps us figure out what L is. because a value of 2 represents the d subshell. And if L is 2, the possible values of M sub L are all the way from -2 to +2. That's 5 possible orbitals. That's 5 orbitals in the d subshell.